Log on, tune in, find out. Another good idea from Cambridge.
So we've already seen Cherednik algebras appear in two talks of Gann and of Gordon. And if you like, I want to make life easy by taking the simplest possible case of what they were talking about, remove all the technicalities by working with the Sn case of our group of Sn. And I want to go a bit further, of course, then, and really try and understand the representation theory of these algebras. So the philosophy here is going to be that if I take the Cherednik algebra, or actually for me it'll be the spherical subalgebra, then you should think of that as a deformation of, you take the polynomial ring in two n variables under the natural action of Sn, and take the invariance of that. So the spherical subalgebra can be thought of as a deformation of that, but it's a ring of finite global dimension. It looks like a non-singular deformation rather than the singular deformation, so it should look much more like a resolution of singularities, which is the Hilbert scheme. So I want to relate these objects to Hilbert schemes and then take that back and use that to understand the representation theory of the original algebra. How far will I get with that in math remains to be seen. And the basic point of this is that a couple of years ago, Ian Gordon and I used a sort of analog of Benson-Bernstein equivalence of categories and work of Heyman on the n factorial conjecture to make this whole thing work. We now have a much easier proof in joint work with Ginzburg, which is what I'll describe, which uses this sort of quantum Hamiltonian reduction that turned up at the end of Gann's talk. So I want to try fitting these things together. So I have a slide here of the notation we had from before. Now I'm not sure if this is actually visible at the back. I can write it on the board if people prefer. Turn off the light. Where is the light switch? Aha. Okay, so this is just reminding you what was going on in the last two talks. I can just leave it there. So we've got a parameter. It could be any complex number, in fact. For technical reasons, I don't want a negative integer, a negative rational number. My group's going to be the Weil group, Sn, just acting by permutations on its natural n-1 dimensional representation sitting inside Cn, just acting by permutations. So with that, I then got reflections, reflection hyperplanes, which I'm calling alpha S, S in S, and the technical thing is the discriminant, which is just the product of all these alpha S's. So then I take the ring of differential operators, or the Weil algebra, so polynomials, ring in the x's and then d by dx's. X runs through z1 through zn minus 1, this being natural basis of h star. And then the rational Cherednik algebra, so this is the HC. Let's write this up here so we can see it. So this sits inside differential operators on H. Or let's call it H reg. So here H reg. So that's H, and you factor out delta is 0, ignore delta is 0. On that, the symmetric algebra acts naturally. You take the twisted group ring, and sitting inside here, we take the ring generated. So we've got O of H and W. So let's write this as this polynomial ring in Z1 through Zn minus 1. So the Zi are a basis of H star. And then the Dunkel operators. We've seen both those two previous lectures. So these would be the D, what's my notation? The Di is D by dZi plus a fudge factor. So you have this constant C, that's my parameter, and then the sum over the reflections, alpha S, the product Zi, divide by alpha S, that's why I need to work on H reg, and then the 1 minus S. So if C is 0, you can just think of this ring as being the Weyl algebras. Naturally, it's a Weyl algebra. And the theorem is that this is actually a deformation of H0. Has the same natural basis. Has a PBW theorem. And so the theorem that goes with that, so the PBW theorem, so this is due to Etingoff and Ginzburg. So we always filter things by order of differential operators. So everything's sitting inside d of h reg smash w, and since w has no differential operators, w appears here in degree 0. So the way I think of the PBW theorem is then that if you look at the associated graded ring of HC, you just get the coordinate ring of H plus HC smash W. So in the last two lectures that were mostly concerning with HC, I much prefer to work with the spherical subalgebra, so that will be UC. So that's just E, HC, E, where E is the averaging idempotent. And if I do that, then again, grade UC is a nice natural object. You're just taking O of H plus H star invariance, or as I'll think of that as O of H plus H star mod W.
You want to divide by the order?
Yeah, that might be a good idea. Thank you. So a typical example to think about here is that when n is 2, take the most simple example. So W, just think of one element sigma. Sigma squared is 1. Sigma z equals minus z. The dc would be d by dz minus c times the 1 minus sigma divided by z. And the uc that I'm thinking about here would be the ring generated by z squared, z dc, and dc squared. And this is isomorphic. So it's easy enough to work out what the commutation relations between these three things are. And you'll find that commute these two, you essentially get that up to some scalars. So you're getting a u of SL2 modulo some ideal I. And this actually runs through all the minimal primitives of u of SL2 as the C varies over complex numbers. And my parameterization is such that u a half is u of SL2 factored out by the Casimir. So, as I was mentioning in the last two talks, Ian and Willian were talking more about HC. I want to work with UC. In my case, it doesn't make really any difference as the representation theory is the same. So the theorem between Ian and myself, and then we had a technical condition that the scalar C was not allowed to be half plus an integer. That's been removed by work of Bezruk-Kavnikov and Etingoff in the paper that was mentioned, in fact, by Ian, which states that under our assumptions, HC is Morita equivalent to UC. And there's only one natural module you would think about, which is you take HC times the trivial idempotent. That obviously is a bimodule over those two rings. And secondly, UC is root equivalent to UC plus 1. So the module here you take is you take E times HC plus 1 times E. Well, if I took that, that's just my UC plus 1. If I multiply on the right by something, in this case delta, that doesn't affect the left structure, so that is a left module over UC plus 1. And on the right, this is a right module over E HC plus 1. So I need a delta inverse and a delta, take account of the delta I had before. And that actually is exactly my EHCE. One of these computations you can do. So that's my UC. So this does require the assumption I've got at the top that I don't have a negative rational number. These theorems are true, except there's a sort of fudge point. There's a point where things go wrong, roughly speaking, corresponding to the fixed point of the Weyl group in this sort of analogy, which is when you're sitting between -1 and 0, these sort of theorems fail. But when they get to large negative integers, they become true again. Okay, so as I say, the way I want to think about these theorems is that rather than thinking of UC as a deformation, so if I took U0, I'd get the fixed algebra, the Weyl algebra, acted on by Sn. But I want to think of it rather than a deformation of that. I want to regard the PBW theorem as saying that it's a deformation of H plus H star mod W, which of course is singular. But on the other hand, by using the PBW theorem and this second theorem here, UC, that's Morita equivalent to HC. HC is just a twisted, or has as associated graded ring, a twisted polynomial ring, twisted group ring over a polynomial ring, so that has a nice finite global dimension. That pulls back, says that HC and therefore UC have finite global dimension. So I should really regard those as being regular rings. And if they're regular rings, then they surely should correspond more to a desingularization of this quotient space rather than as something like the quotient space itself. And that's where the Hilbert scheme comes in, because we want to think of, so combining these results, so by theorem 1, UC is deformation of my quotient space. Maybe I won't be so lazy, I'll put the O in there. And then by theorem 2, it should be a smooth. If you like, this is a non-commutative deformation. So as such, it should be more like the Hilbert scheme. So this gives a nice, technically a crepant resolution of the quotient space. So here, if I think of Hilb n of C2, so that's all ideals I sitting inside the polynomial ring in two variables, with the property that the quotient has dimension precisely n. So the dimension of Cxy mod I is n.
What do you mean by smooth in the non-commutative?
I was hoping nobody would answer that question because I've got no idea. What does smooth mean? Yeah. So commutative case, we all know what smooth means. A million definitions are all the same. The non-commutative case, the different definitions of smoothness all have different generalizations. And So let's say something like, I think actually the definition of smoothness, ironically, there are three conditions. There's finite global dimension, there's being Gorenstein, which in the Auslander sense is actually in some sense stronger than finite global dimension. That if you define Gorenstein in terms of X groups. And there's the Cohen-Macaulay condition. And if you have analogues of all three of them, then somehow you get the right concept, right sort of properties that you would expect of a smooth algebra.
Yeah.
I don't want to talk about those here because it's.
So if you take any finite Coxeter group, you will still get a smooth and a set deformation, even though in the classically you don't have a smooth deformation.
You mean providing I've got this sort of equivalence of categories? I mean, I need to get something.
It is not proved, but conjecturally all of this is true for any finite Coxeter.
Yes, and where C is sort of big enough in some sense. Yeah. So in those cases, I would expect these rings to be smooth. I have to worry. I mean, I have to be in a situation where I keep Gorenstein. That would worry me if I didn't have Gorenstein. But we've got some. We're okay because we've got some technical affections.
Was a graded algebra?
Yes. Yeah. So I think that's where it would. That's probably where it would sit. So yes, a conjecture you can ask as you go through is how much of this can we generalize? The answer is I have no clue, but I'd love to know the answer. Okay. So we've got something that looks more like a Hilbert scheme because that gives this nice Crepin resolution, so this nice resolution. So this is supported on n points with multiplicity, so I just go down to corresponding n points without regarding order, and that I can think of as C 2n mod W. So I just take my n points without regard to order. Well, that's not quite right. We're supposed to be dealing with little h, which is the n-1 dimensional representation, but that's no big deal. So we're just using, so if I call this map pi, I want to have h cross h star mod W. So I just take pi and pi inverse of that. And that's what I'm going to be thinking of as the Hilbert scheme. So I'll write that as Hilbert brackets n. So this thing is very harmless doing this. Really what one's thinking about here is I'm talking about n points in the plane. Well, by taking this set here, I'm really just saying I'm going to take n points in the plane, and I'm going to fix the center of gravity at being the origin. So it's a completely harmless operation. Okay, so given I want to think of this algebra as being more like the Hilbert scheme, I have to put some content into that and say that I can pass from my algebra UC, when I go to the associated graded ring, I somehow want to end up with the Hilbert scheme, not the quotient scheme, the quotient variety. And the sort of picture that gives us the right analogy for that is Baylis and Bernstein. So there we're thinking of U of G mod P, P a minimal primitive. Yes, there are. What are they now? I mean,
But they are not smooth.
some of them are not smooth, so you get problems there.
So type B, they are smooth. They're not smooth. Yeah.
Yeah, so you don't have these nice resolutions in particular. So here we should think of this as having associated graded ring, which is the coordinate ring of the nil cone. And for that we have the Springer resolution. So T star of G mod V. And we fill this diagram out by taking differential operators on G mod B. Baylis and Bernstein says you've got an equivalence of categories there because you can identify this with global differential operators on G mod B. And again, taking grade. So in our situation, so this is a question of Ginsburg and Kaledin, you want to do the same. So we've got our UC, taking grade, we've got O of H cross H star mod W. There our desingularization gives us the Hilbert scheme. So I want to fill out my diagram. Okay, so first of all, I mean, for SL2 case, for the n equals 2 case, this is done, because of course we've just got factors of the enveloping algebra. But once you get past SL2, or S2, you don't have anything like a cotangent space, so that just doesn't work. But there is another way of thinking about the Hilbert scheme. Just think about this more ring theoretically. You think of the Hilbert scheme of being proj of the appropriate graded ring, and I would then use that graded ring down here, and then I want to fill in the diagram. So the graded ring we take, due to work of Heyman in particular, it has a particularly nice description. So I'm going to take A0 to be this ring. So if I'm desingularizing, I'm blowing up the singularity, so I should think of that as take a Rees ring of the appropriate ideal and then take proj of that Rees ring. So that means I just want to take an ideal in here, take the associated graded, the direct sum of powers of I, and then take proj of that. And that actually is particularly nice, where the ideal you take would be you just take the anti-invariance. And then you take A to be A0 plus A1 plus A1 squared plus A1 cubed, and so on. Of course, this is not in there, so it's not an ideal, but I can always just multiply by any anti-invariant to make it an ideal. The natural one to take is the discriminant delta. So I just multiply A1 by delta, that becomes an ideal. I take the Rees ring of that ideal, and then I take proj of that. So I guess this is much older than Heyman, but he's the one who's really given us a thorough understanding of what this sort of ring looks like. So then proj of A is just the Hilbert scheme. So that's translated the commutative side to something that's purely ring theoretic, which really has to be the situation I'm in the non-commutative side. So then I can ask, well, what about the non-commutative side? Well, again, I'm in trouble if I just try to follow this idea naively, because generically, or even when C is 0, and for generic values of C, the rings HC and UC are simple rings. So they've got those two-sided ideals. I've got no chance of forming a Rees ring. And that actually is a phenomenon that happens a lot in the non-commutative case. You don't have ideals, but what you do tend to have are lots of bimodules. The rings change, but they tend to be meter equivalent, and the rings are meter equivalent by various bimodules, and you can sort of use those in place of the ideals. The case of the analogy with enveloping algebra case is if you think of the translation principle between various factors of your enveloping algebra, that you can think of as tensoring with a bimodule over the two corresponding factor rings. The equivalence of categories gives an equivalence of categories, therefore means the bimodules are progenerators. And that's exactly what happens here. So the non-commutative side, you remember the UC and the UC plus 1 were equivalent by a bimodule, and I can go from U to UC plus 1, UC plus 2, and so on. I take all those bimodules, and I can sort of think of those as trying to be these ideals, and products of those being the products of the ideals. Of course, each time I take a product, I've got a different ring as the endomorphism ring acting on the other side. So about the only way I can put those together is a great big matrix ring. So these are called Z algebras. Not really quite sure. So I do this, the following ring. So direct sum Bij, I greater or equal to j, greater or equal to 0, which I want to think of as an enormous lower triangular matrix ring, starting at 0, and then B1, 0, B2, 0, B2, 1, and so on. The BII's, those are the UC plus I, so UC plus I is my BII. The B10 is then the bimodule I had between these two, so that would be the EHC plus 1 delta E, that's the appropriate bimodule I have there. And then, in general, the other BIJs are the progenerators I get between the two diagonal entries coming from that theorem. And then, given I write a ring like this, you can guess how you multiply things out. You just use matrix multiplication. And the way these things are cited is precisely the way you define the bimodules for U, I, C plus J as I and J get bigger, just by taking products of small ones. That's exactly how you multiply together two matrices. And so then the theorem we want is that, if you like, that works for my question mark. So
I suppose you tensor over
you tensor over whatever C works. So here, going from these two multiply to that one, you'll multiply, so this, it'll be the U C plus 1, C plus 1. Because, you know, if you get B1, 2, 1, B1, 0, the 1 here means that this is going to be a right module, this is a left module over the UC plus 1. So it's just what you're forced into the right definition, basically.
Actually, a question. So this Bij just change the product of this, of the bimodule
Yes.
theorem. Is there a way to write it down in, somehow like this, so in explicit way?
Yes and no. No in these circumstances, except, I mean, tensor products are the same as multiplying, because I've got projective modules. So yes, I could multiply them together up in the ambient space, differential operators on H reg star W, but I've no idea really what I get. It's hard to see what you get. In 10 minutes or so, I will give another definition of these objects, where, in a sense, I do have a natural way of writing it, but it's in another space. That's the yes as opposed to the no. Okay, so what have we got? So first of all, we started with our U, and taking modules over that, that's the same as modules over B. Well, not exactly modules over B. I should take modules over B, certainly finitely generated ones, because I want finitely generated ones over U. And then I'm going to take the modules over that's a real mess. This big ring is far from Noetherian. But the natural modules I take are just column vectors. which I think of as being naturally the graded modules over this. That's still too much. I should look at Q-grade of that. So as in the commutative case, when you're taking proj of a graded ring, you ignore the finite dimensional modules. So here, I'm doing exactly the same for this. I'm taking B Q-grade, so this is equal to graded, finitely generated B modules, modulo bounded ones. So as I say, I'm thinking of these as column vectors on which this acts. That's naturally graded by how far down the column you go. And the bounded ones, those are just the column vectors that become eventually 0. And the map here is just tensor product. So that's a fairly easy theorem. That's easy. Just follow your nose and you'll see you'll get a proof. So that gets us to B. Now from B,
Regular Z statement, right? Statement 2.
yeah, essentially it comes. It's that does it for you. Statement 2 then is once I got across to B, I can take associated graded objects. Again, these Bij's, everything sits inside this big ambient ring of differential operators. So I've always got the order filtration. I just filter this everywhere, and then I take grade of B, and then I get what I'll call A hat. So this is not quite the A, because that was a graded ring. But out of a graded ring, you can always get one of these Z algebras just by taking the A, J minus I, or taking the A delta 1 to the I minus J, and taking that in the IJ, the appropriate diagonal below over there. So this will be I greater or equal to J greater or equal to 0. So A0 goes down here, A1 goes down here, and so on.
So in particular, powers of this thing and tensor powers of this thing are the same,
Yes.
which is a non-trivial field.
So there they are.
What about
Here I'm only taking powers. Here I'm not taking tensor powers.
tensor powers will not be the same.
Tensor powers will not work here because these things are not projective.
That's right.
So that's where you have to be careful. In the non-commutative case, you see, life is easy. Everything's projective in life. So think tensor powers and powers are the same, so you don't have to worry. These commutative ring theorists have much harder life. So once I've done that, then I can take grade of... So I take grade of B, and then I take Q grade of that in exactly the same sense. So this statement says that's the same as the A hat Q grade. If you look at the A hat and the A, you find, in fact, they have not only the same Q grade, they have identical graded modules. So that's the same as A Q grade, which by that Heyman result is nothing more than coherent sheaves on the Hilbert scheme. So that fills out this diagram. So this is my B Q grade. And I suppose since I've got category modules here, I ought to put mods everywhere. And then I suppose I should put coherent sheaves here. Now at least the statement is well defined. Okay, so that's the main point of the talk, is that we have this construction. Now, Ian and myself, our first proof of this was that, what do? You look at the objects you have. So this again is easy. Once you've got Heyman's results above. So it's this part which has the real work. And the first step of this is easy. So if I take this, the first diagonal, these EHC C plus J delta E, and I take grade of that, then it's easy to see you can pull the delta out, and you do indeed get A1. Delta, that's easy. And then looking at products of these things, which is what I'm trying to get for the other HBs. Now let me see. The product of the grades sits inside the grade of the product. And typically those two are going to be very different because, of course, when I'm taking a product in the non-commutative case, I've got commutators floating around, which you expect to give a lot more other things. So you expect that the grade of the product is not equal to the product of the grade. Sorry, yeah. So you expect those two things are not equal. But that's exactly what I need to be equal to get this statement. So there's subtlety at this point, and that's where the hard work comes. So the proof we had originally was that we looked at the two sides of this for higher j's, for the higher terms, and we computed Hilbert series. So the non-commutative side, that comes essentially from the Hilbert series of Verma modules. On the commutative side, it comes from Haymann's work. You've got two things inside each other. The Hilbert series are the same. The modules are the same. End of proof. Slight problem is your things are all infinite dimensional, so you have to work with factors, but that's not a big deal. But what I'd like to give today is a second proof, which is much easier than that, and is based on work of Gans and Ginzburg, and the concept which you saw very briefly at the end of Gans' talk, which is this quantum Hamiltonian reduction. So taking radial components. So this is with Ginzburg and Gordon. So quantum Hamiltonian reduction. So how does that work? So we're taking V to be Cn, on which GLN acts. And we have the Lie algebra GLN. So the classical case, so this goes back to Harishchandra. So what have we got? We've got G acting on V. So G acts on differential coordinate ring and then differential operators on V. So then you can take, oh, actually, I'm not going to take that. I'm going to take G. So then we have D of G, G. So restriction of functions. That maps you to differential operators on the fixed ring. So invariant differential operators act on invariant functions. So this acts on differential operators on O of GW. And then what I'd like to have is
of H, right? Of H.
G of G, G. So that's the same as O of D of O of H, W. So what I'd like to have is pull the W out. So I'd like to have differential operators on H, W. That actually, it doesn't end up in here. But you can you can shift your operators. You can twist your operators slightly by conjugation, in fact, by delta. So this is a twist. And then the whole map you have here, what shall I call that? Do I want a name? Phi. So then Harishchandra and Wallach. So Harishchandra noticed that this proves that this map actually is well defined. The image really is inside here. And then Wallach noticed that it's rather easy, in fact, in that situation to show that this is surjective. And Levizier and myself showed that the kernel of phi is, so G here acts again on this by differential operators. So inside here, we've got G sits inside the derivations on G. And the kernel of this map is you just take that g times d of g, and then you take invariance. Too many g's in one word. So we want to do the same and get the ring UC in the same way. Well, we have to make things a bit bigger. I need the extra freedom to get this C. And we do that by taking E to be V cross G. Again, with its natural action of G. So now, with Gann and Ginsberg, you think now of D of E fixed by G. So this acts on the det C isotypic component. Of my O of E. So this gives us, and that, by the way, is isomorphic to just delta to the minus C times O of E after localization. At least locally it looks like that. And then again you get a map then from D of E G to differential operators. And again you have to twist it, but now you don't end up with this ring, you end up with UC. So after twisting, so this gives a surjection from here to UC, and the kernel.
We are not assuming that C is an integer.
Nope. No, they do it in general. They have enough extra. You get enough extra freedom to do this.
So what does that C isotypic?
So the ones on which the determinant acts, the central element of GLV acts by.
Which is 0 when C is no integral.
No, but what you
Well,
need,
C
you
is a
need to
positive
take multi-valued functions. Yes?
No.
C is not.
Got problems when C is positive. No, this is okay.
Well, that to the C is not a representation of G.
Yeah, so you're claiming this is not in here unless C is an integer. Not unless it's a rational number. That's okay. I'm not messed anything
Okay.
up. I'm not messed anything up. I think we're okay. And the kernel is IC D of E G for IC is SLG plus U of G, and then you take the identity matrix, maybe I should double bar, minus C minus 1. So the SLV acts trivially, and then the identity matrix of GLV acts by a certain character. I got this right, haven't I? It's your theorem, so that's I found you. Okay, so now the key point I want to do is play games with the AIs. And for those I need isotypic components, so I'm going to take D of E over D of E I C plus 1. And I'll take the det component of that, and I want to claim that this is my E H C plus 1 delta E. So what's my proof? Well, both sides here are naturally, so U C plus 1 UC bimodules. We saw how it worked there, and the same thing works on the left-hand side. And they sit naturally inside the big ambient space. Or maybe actually I want to be a bit smaller than that. So I'll say the quotient space of U, ring of fractions of U of C. So you really think of that as being D of H fixed by W. So the problem with this is that these two things are coming in completely different directions. One's coming from the quantum Hamiltonian reduction of Gann and Ginsberg, that's the left-hand side, and I've got no real idea what this looks like when I look at its natural image in here. And on the right-hand side, I've got the things coming from the rational Cherednik algebra. But when I look at the images, I notice that they are actually reflexive on both sides. In fact, they're even projective on both sides. And the theorem is there's only one such object. So the analog of this is if you take a simple ring, exercise for you to prove, take a simple ring and look inside its division ring of fractions, simple domain, and look inside its division ring of fractions. And you say to yourself, well, how many bimodules do I have which are finitely generated on both sides over my original simple ring? The answer is 1, which is the ring itself. So that's what's happening here. Once I've got that, then I'm home. So now you see, if I take my B to 0, so that would therefore be the D of E over D of E. All your numbers get shifted, so this would be a C plus 2 det D of E over D of E U I C plus 1, again det. So that's what we get for the product of our two things from the right-hand side. That's rather easily seen to be the D of E over D of E I C plus 2, where I take a det squared. So this is all work again in Gann and Ginsberg. And this has associated graded module A1 delta squared. So then you induct. So that gives the result. So this answers your question in the sense that if I'm working on this side rather than this side, then I know what my products are. You just naturally take powers of debts. There is actually a problem with this proof. The statement I made about the Weyl algebra, I lied, of course. There are two modules for a simple ring, which are finitely generated on the two sides. One is the ring itself, and the other is 0. That's actually 0. So what you have to put is a -1 in there. That switches it around to a delta to the -1 there, and a C -1 there. That's not so bad. That actually is the EHC plus 1E dual. But now to unravel the duals, you have to work with you're getting your sides wrong, so you need to switch sides, and that really means going, or taking, if C were a negative, I'd be okay, because my sides would now be the other way around. And you can go to C negative, which is you use that my UC is isomorphic to U minus C minus 1. There, the sides now have swapped over in a sense, and everything works. And then the proof goes through. So what I want to finish with is, so that proves the theorem. What I want to finish with is an application of that to looking at modules.
Does this work for symplectic reflection algebras?
I wish it did. I don't know. I only know how to prove this for type AN. I mean, I suspect if we're taking the situations that, you've got the complex reflection groups that Gam and Gordon were thinking about, then maybe the same sort of thing would work there. Because they, as Gam was saying at the end of his lecture, you do have this Hamiltonian reduction there. So maybe one can get this proof to work. But this is the only case I can prove it.
We don't really know as much about the Morita equivalences in that case, but suppose we know, for example, for type B, that for positive C you have Morita equivalence between C and C plus 1, and with spherical subalgebra. So,
You mean by C and C plus 1 and case B? Two parameters.
right. Well,
So you go along spines.
You take equal values on all equations.
Yeah.
And suppose you know that, and would modulo Z this thing work in that case?
I can't do it, but I presume it will work. You sound like you know it works. I don't think.
Yeah, it's in the thesis of one of my
Ah.
It's in the thesis of one of my theses.
Ah.
But going through to.
If you assume what Abel
Okay, sorry. Yes.
Because it is still not known that for positive C you have E, H, E.
These products is like
Reef product, sorry. So the whole Gam-Gisberg stuff goes through that. So what about a further complex reflection ones? Or is that still unknown?
I don't know what happens if you shift in more general
Yeah.
directions.
But in some sense, this shifting is not so important because you can just take the B rather than the A and work there. And that just says that, well, once you shift far enough, you should be okay. And that will give you data. So I think in that sense, in principle, it should be okay. Okay, so I've got to mention the title of my talk, so I have to do a little bit more. 5 minutes, fortunately. So the application I want to talk about was representations of modules, of the representations of the algebra. Representations of modules is a bit too far. So the idea should be that rather like with Benson-Bernstein, you can pass through to the coordinate ring of the cotangent space of G mod B of the flag variety, and then pull data back to representations of the enveloping algebra. So here, I want to say that I want to use this theorem to go down to the Hilbert scheme, and in particular the sort of information that Heyman gives us there, and pull that back to tell us information about the representations of UC and then HC, because they're Morita equivalent. So the way we do that is we start with M, let's say lambda, a filtered UC module, or I could start with HC. Then I go to B tensored M tilde. And here you use the tensor product filtration, the induced filtration basically. And then I can take grade of that. That gives me a module over this A hat, or equivalently over A. And then I can go to proj, and I get a module, or coherent sheaf, on Hilb n. And the natural thing then is you take the characteristic variety of grade of M. So that's the support. I call that phi then. So the point of the talk was to talk about the fact that if I start with a simple module, this actually gives me an equidimensional variety sitting inside the Hilbert scheme.
And do you mean simple module in category O?
No, any simple module. If I'm in category O, so if L is a simple, or any module in category O, so the same category O we were talking about before, so you look at modules on which the Dunkel operators act adnopotently, and then you look at W acting naturally, and those are the modules in category O. So you can think of these as you take the Verma modules and take the factors of those. So if L is any module in category O, then in this way, the characteristic variety of L is equidimensional. Dimension equal to H. And you can more or less write it down. I won't do so now because it'll require too much time. But let me just tell you why in this situation equidimensionality is particularly easy. And that's because we go through the process of Gann and Ginsberg. So I've defined the variety, associated variety in terms of B. You can also define it in terms of quantum Hamiltonian reduction. So you take your module, you do the opposite of quantum Hamiltonian reduction. You tensor up with this object, like that. That gives you a module over D of E. There you take the associated graded ring. That sits naturally, in fact, inside the inverse of the moment map, inverse of 0 under the moment map, and that then gives you, at least on an open subset, a principal GLN bundle over the Hilbert scheme. So you can, from a slightly convoluted way around, you get to the Hilbert scheme, the two things are the same. But if you do that, this sort of statement becomes rather easy, because Bernstein's dimension formula works. We take my module, I pull back, I've got a module over a ring of differential operators. Its dimension there is half the dimension of the ambient variety. Passing to open subsets and taking GLN variance doesn't really harm those sort of things. What you end up with down here is, again, a Bernstein-type inequality. The dimension, the characteristic variety of L for any module over UC, all its components have to have dimension at least this. So that will give the answer to that. So there, since I ran out of time, is a very brief proof of the theorem. But as I say, you can do it for arbitrary modules by going through the ring B and using Gaber's other proof, which is his version of equidimensionality there. But it's a more involved proof. Thank you for your patience.
Any questions? So it's a bit puzzling that you don't get bigger modules, right? A simple module?
So here,
Yeah, I mean, if you go outside the category O, you should have bigger ones.
so outside the category O, things become much bigger, yes. I mean, after all, I can take the ring itself, and that will give me something of dimension 2h.
Oh, I thought
2
you
times
were
the
saying
dimension.
that this argument goes through.
So what it says is that for any module, the characteristic variety, the components have dimension at least equal to the dimension of h. They can be bigger. For the ring itself, of course, I would get twice this number. But it's exactly the same as what happens with Benz and Bernstein.
Yeah, basically, all modules are holonomic from this point of view.
Category O modules are holonomic.
Yeah, that's right. But I misunderstood what you said. Any more questions? Yes.
So for category O in Bernstein-Berenson, there is some relation with Schubert varieties. Do you have something like Schubert varieties here or something like
Not yet.
intersection cohomology?
Not yet. No, I know nothing about that side. Have you tried doing it?
Question: what is the main idea of proving this sort of inequality of Bernstein? Just in one sentence.
For me,
Point, yeah. Because
here, well, so I start with L, I tensor up with this d of e. So there I've got a modulo over d of e, and I know its dimensions. This actually, and then I take grade of that, and I take its characteristic variety, and that sits inside the inverse image of 0 under the moment map. And then that is a principal bundle over the Hilbert scheme. So I mean, here I know my modules are big. So here their modules are still big. Taking principal bundles, I'm just taking SLN or GLN invariants. We know how that diminishes size. So at each stage, I'm just counting the dimension I know I must have, basically from Bernstein's theorem. So it's not, unfortunately, it's not a very interesting proof.
Basically, it says that if you have a ring and bigger ring, which is finitely generated module, it is the Gelfand-Beal dimension can go up. Basically, this.
It's that sort of result.
Yeah.
So it uses that this variety is quasi-curve.
Yeah.
Yeah.
But this doesn't mean that modules, the Bernstein inequality for modules is not satisfied for Cherednik algebra in general. Because there are, for example, finite dimensional modules. But the
But
dimension.
it's simple. It's simple. Algebra is
Yeah.
simple.
Not for all C, only for generic C.
Yeah. So I mean, there's a subtlety here. When I'm over, in category O, modules have lots of different dimensions, from 0 up to the dimension of h.
It doesn't have to be equal to the dimension of H, it could be less.
Yeah. But that's true.
It's simple.
Not for all C, only
Not for
for
C.
all
But
only out-
theoretically, they have dimension, all have the same dimension h. This is what happens in Balance and Bernstein. You take modules over the enveloping algebra. When you think of them, look at the sheaf of modules of differential operators. Sheaf of modules over the ring of differential, sheaf of ring of differential operators. There, the dimension is at least the dimension of the ambient state.
I mean, tensing blows up the mod.
Yeah.
Any more questions? Well, let's hand the speaker once again.